hydrogen atom that is 1 millimeter in radius. Is it obvious from the get-go it's going to be a very high quantum number? Because an atom is a little tiny thing. For it to be this large, it has to be an extremely high quantum number. So, I did it really from the information that we had primarily on the Bohr model of the hydrogen atom handout, whereon you find that the nth radius is given by n squared times the quantity epsilon naught h squared divided by pi m z e squared, pi m z e squared. And I noticed, of course, we're dealing with hydrogen, and if n equals 1, we already know that radius, don't we? That was given in class. For r sub 1 is going to be, well, 1 squared times 0.53 times 10 to the minus 10 meters. So, of course, what's in parentheses here is what's in parentheses there. I saw many of you recalculating this value. That is not incorrect, it's just a little bit slow, that's all. So, n is going to equal r over this thing, and forgive me for not writing it, under the square root, which, what did I say, 1 times 10 to the minus 3, divided by 0.53 times 10 to the minus 10 under the square root, and I got 43. If you went ahead and calculated, it depends on how you round and get a number very close to this. Might not be exactly 43, but it'll be close to that. Now let me tell you something, folks. People who just barely get their homework done, they'll always go back to the fundamental way and do things the hard way. If you're really aware of what's going on, you say, well, I know that number because I know when r is equal, when n is equal to 1, I know what r is when n equals 1. So I've already got a numerical value for this, which even includes the correct units. So this is a cakewalk, right? If you do it this way, if you know the way to do it, if you're really familiar with the problem, this type of problem, nothing to it. Is n large? Just like I expected, n is large. Now the next part of the question read, what's the energy of an atom in this state? Well, the energy is given by E sub n equals minus 1 over n squared times m z squared e to the 4th divided by 8 epsilon naught squared h squared, 8 epsilon naught squared h squared. And hopefully by now you're starting to think to yourself, hey, have I got a value for this thing? Yes. On the handout, they give you a value for E sub 1. E sub 1, which by the way, you have to convert it because it gives it to you in joules, but when you convert it is, let me put it down as minus 1 over 1 squared, just to make a point. And then this is 13.6 electron volts. So yes, you can calculate it if you want. It's the long, hard way, but you can calculate it if you want. So E sub n for us is going to be minus 1 over n squared. For us, what was it? 43 squared times 13.6 eV. And I get minus 7.2 times 10 to the minus 7 electron volts. And I thought it would take you just that long to get those two answers. 4 minutes. It would take you just that long. Now comes the important part of the question. The important part of the question said, why is such an orbit unlikely to be occupied? And I thought about this for a long time, and I thought, you know, in a physics class, we've got a laboratory associated, we're very numerically oriented. There is a verbal answer, and then there is an argument to convince people that your verbal answer is correct. Let me start with, is anybody willing to give just a verbal answer, and then I'll go on with an argument that I would very much like to see. What would you say?
The energy is so low that any little amount of energy will change its orbit.
In fact, better than that. Almost precisely correct, but even better than that. Yes, essentially, look at this incredibly, now we are bound. The negative sign means bound, right? So you have an electron that's bound with an incredibly small energy. Any little abuse will knock the electron off, won't it? In fact, the first thing that occurred to me, and I wonder if this would have occurred to you, I hope it would. Maybe not instantly, but I hope after a little bit of thought you would ask yourself this question. How much energy is there in thermal impact? If you've got a hydrogen, a sample of hydrogen gas, in this energy state, at room temperature, how much energy is involved at thermal temperatures? What is the translational kinetic energy at thermal temperatures? Does the question make sense to you? If you've got these gases, they're banging into each other with a certain amount of energy. I'll bet you that the energy is significantly larger than this. But we're not supposed to bet you in physics. We're supposed to calculate. So I calculated how much energy there is in thermal impact at room temperature. Ke equals 3/2 kT. So the kinetic energy that I got was 3/2 times the Boltzmann constant, 1.38. No, it was 1.38 times 10 to the minus 23. 1.38 times 10 to the minus 23. And of course the units are joules per Kelvin. Joules per Kelvin. And what's a nice, easy, approximate room temperature? 300 kelvins. Except this won't quite work, will it? Because now I'm going to be comparing a number in joules to a number in EVs. So let's right now, let's convert this thing into electron volts. Several of you asked me this question. Just remember, of course, an electron volt is a little unit, a joule is a big unit. And the numerical equivalence is the charge on an electron. So you shouldn't ever have to look up or ask anybody any questions. You should say, 1 electron volt is 1.6 times 10 to the minus 19 joules. You should be able to say that and write it down, no question in your mind at all. And now, of course, kelvins will go with kelvins, joules will go with joules, and you have electron volts. I calculate this to be, why don't you check me right now, 0.07755. 0.077 eV. I'm pretty sure that calculation is correct. You can either just nod or thumbs up if you like. If you agree with my answer, shake your head down or thumbs down if you disagree with my answer. Don't do anything if you're not checking. Go right back to sleep. Sorry, you won't be. Anybody get this number? Nobody got that number?
No.
What did you get?
0.0477.
0.0477. Is that what you got?
Someone else got different.
let's see here, let's just for the fun of it,
I got 0.0. I got what you got.
3 halves, 1.38 times 300 divided by 1.6 times 10 to the minus 23, and then you bring up 20, so that's minus 4, isn't it? So this should be the only calculation you're doing in your calculator right there.
0.0388.
You get 0.03? 8, okay, so my calculation went awry somewhere. Thank you for checking it. And it doesn't matter very much, does it?
No.
In fact, as soon as you see, look, as soon as you see this and that, you have answered the question, haven't you?
Yeah.
The details of what goes into the calculator, physicists, if we're within an order of magnitude, we're happy. All right? But clearly, the energy, the thermal energy of the atoms is far higher than the binding energy. So this thing would be knocked apart instantly. Right? And you don't have to worry too much about your calculator. You look at this number, and you look at that number, and you say, whoa, I got a ton more thermal energy than is necessary to ionize this atom. So that was one thing that verified. You know what I did just for fun? Have no idea what I do for fun. A guy like you have no idea what you do for fun. What I did was I asked myself, how cold would the hydrogen sample have to be to have kinetic energies equal to or less than this binding energy? Does the question make sense?
Yes.
How cold would it have to be? So all you do then is to put in this energy as your kinetic energy and solve for T. Would you do that right now? And see, I did this calculation very, very quickly also. And so when I solved for T, I ended up, of course, with T is equal to what? 2/3 times the kinetic energy over the Boltzmann constant. And, by the way, kinetic energy is 7.2, 10 to the minus 7 eV. Bothered the calculation of what the Boltzmann constant is, 8.617 times 10 to the minus 5 EVs per joule, EVs per Kelvin. So I converted the Boltzmann constant from joules per Kelvin to EV per Kelvin because you might use it again sometime. This conversion number here can be written on the inside cover of your book and used in the future if it's more appropriate to work in EVs than it is to work in joules. And then I got a final temperature of 0.0054 kelvins. Did you get that? Did you get that number out of this calculation?
I got
Anybody try it?
I didn't get it. Did you get it?
Please check me out because
It's like 0, 0, 0.
it seems like I was off by a factor of about 2 something there. Oh, I just put in the same amount of kinetic energy. So what if I had this amount of kinetic energy?
No.
So if I put that amount of
No,
kinetic energy in an ionized
Point
state,
0, 0, 0,
so I'm saying how much temperature is equal to this
Let me
much
do it
energy
again.
as kinetic energy. Anybody do this calculation?
No.
Did you get this number?
Yeah. 5.6.
Didn't get that? What did you get?
008.
56.005. You're going to say you disagree? Okay. So, 0.00, and by the way, that's what I put it down. I said, so the temperature would have to be 5 millikelvin. Millikelvins. 5 millikelvins. Okay.
You said you did that one cooling experiment where it took like a week to cool down to temperature?
It took a week to get down to 88 millikelvins, and this is 5 millikelvins. So this is almost impossibly low temperature. It would be very difficult to even achieve this temperature. But all of that, from here over, is to justify your answer at the bottom.
Yeah, I totally.
As scientists and engineers, you can't just make verbal statements. You must justify them. So, unlikely, why? I expected you to say that because this is a very weakly bound electron. And then I would like you very much to justify the answer. To just say it's a weakly bound electron is just the start of the argument. And then you say, look, at thermal energies, you have way more than enough energy to ionize the thing. That's why it's very unlikely to be occupied. Because I have to be at this temperature or lower before the thermal energy would have gone ionized. So as scientists and engineers, you've got to make numerical arguments, not just verbal ones. The verbal ones are a great place to start and then justify. However, I won't be too picky when I'm grading this quiz. If such a question is asked of you on a final, however, I will be picky. Okay? So make a note of that. Make a note of what we did and say to yourself, if I do this on a final, he will be picky. Good. Because you'll probably get to use your notes on these finals, and if that note is in there, it will remind you on the final to justify these claims. All right, what's next? A couple of announcements. First off, we have 2 more labs. Both of them are computer labs. I handed out a piece of paper with the web addresses on it, wouldn't I?
No.
Okay, I'll find them and hand them out to you before today is over. There's 2 more to go. One is called the oil drop experiment. Most of the time it's called the Millikan oil drop experiment. And that is also an interactive lab like the photoelectric effect was. Remember we did the photoelectric effect as an interactive lab with actual measurements with a hypothetical photo apparatus. Well, that's true for the oil drop as well, the Millikan oil drop. So I expect you to read about the Millikan oil drop, understand the purpose of the Millikan oil drop, then go do the experiment, and then do a write-up. And some of you in the photoelectric effect, you did not give me an answer. In summary, you said something about, well, this was pretty accurate, or it was close to within so many percent. But what was the answer? Remember, the summary has to have the numerical value in it. And then whatever conclusion you want to draw. So please don't do it this time like you did the last time. Last time you turned on the computer, you played with it for a little bit, and then you went home and tried to figure out what you were doing. What do they call that? Bass backwards? That's all wrong. The correct way of doing it is read about it, try to figure out what's going on, understand the experiment before you turn the computer on. This is not a game that you figure out while you go along. You've got to know what's going on to begin with. So read about the oil drop experiment. Like I say, most of the time in the literature you find it under Millikan oil drop experiment. Robert Millikan, the man around whom they built Caltech. I'll say that again. He's the man around whom they built Caltech. A very impressive fellow and a very impressive experiment. Now the second one, the Frank Hertz experiment, I don't think it's interactive. I think all they do is they describe it to you and show you some pictures. So really the Frank Hertz experiment is really a report. You're giving me a report. Here it's a lab, here it's a report, where you just try to understand what the purpose and what the final measurements were on the Frank Hertz experiment. What's the purpose, how do they do it, and what's the final measurement on the Frank Hertz report. So this one is a report, this one is an actual lab. And this is really critical. I'm organizing all of my plans so that I can get finals finished and grades calculated on time. Therefore, I have to have everything for lab finished by the end of this month. Notice I call it a drop dead date, because it will be. You don't turn it in on the 30th, you come to me with it on the 1st? No credit for that at all. 2 questions. First, Christina.
You mean April, not May.
Did I say May?
Yes.
Yes.
Okay, thank you. May. Or I would drop dead. Is that what you're pointing out to? Yeah. And what year is it?
No, I don't
Oh,
know.
yeah, April, thank you.
Year 2013.
What year relative to what?
According to the Mayans, it's late.
According to the Mayans, we should
Or
be
the
dead.
Chinese calendar, 2040.
And I think I told you guys about the experiment I did in 1972. And I wrote the date, hundreds of times every day I was taking data. And every time you take a sample, I was taking samples of fish. You can imagine. Every time you take a sample, you put it in a little envelope, put a date and time down, what time you took it. And I wrote 1972 so many times that if I'm not thinking, I still write 1972. Still today, I write 1972. So thank you for noticing that. Okay, so the labs due the end of this month is a drop dead date. I have to be starting my calculations for laboratory by this date. 1 day late, and I've already done all the calculations. I cannot accept this. 1 day late. It's a drop dead date. Not please get it done. Drop dead date. All right, 2 quick topics. 1, what is a laser? Light amplification by the stimulated emission of radiation. You might imagine that if you have an atom ready to divest itself of energy by producing a photon, that it is an oscillatory system which oscillates like, in Physics 4, did you see the film of the Tacoma Narrows Bridge? Everybody sees that. It oscillates a little bit like the Tacoma Narrows Bridge, and if an energy source comes by of exactly the same frequency, then a resonance will occur. So if you have an atom right here, which is oscillating at a certain frequency, ready to divest itself of the excess energy, and along comes a photon of exactly the same frequency, there's a resonance between the two. It will stimulate that atom to decay and add its energy to this photon precisely in phase. So you get perfectly constructed interference. Now imagine you have a whole line of these atoms with exactly the same excited state, all ready to divest themselves. A photon comes by, it picks up one from the first atom in perfect phase, the next one, the next one, the next one, and then the laser beam turns out to be monochromatic, coherent electromagnetic radiation of extreme intensity.
Does that mean the further the laser goes, the stronger it is? So like,
Yes, that's why very often you'll find that lasers have 2 mirrors at each end and they actually send the photons back and forth. But the real trick, ladies and gentlemen, is finding a material that has a metastable state. And let's say that this is just some lower state, perhaps it's n equals 1, the lowest energy state. If you pump this thing up to some higher state, and notice I've gone up at least 2 steps, and then it quickly decays from this upper step down to this step down here. Quickly means typically 10 to the minus 8 seconds. That's how long an atom will stay excited. And it strikes this state, and for some reason, this state is what we call a metastable state. Look, this is a very long-lived state. 10 to the minus 6 seconds is a long line. So, you pump the atoms up, they decay down here, and they sit here for a while until a photon comes by that they can add their energy to. They come back down, then you pump them back up here, they rest here, the photon comes back, they add some more energy. They decay, you pump them back up, the photon goes back this way. So as the photon goes back and forth through the system, it keeps stimulating the atoms to add their energy. But the key is, number 1, it's exactly the same wavelength or frequency, and the energy is added in perfect phase. So you get pure constructive interference. Laser, light amplification by the stimulated emission of radiation. And it's contingent upon having the atom in a state ready to decay at the photon's frequency. So I just wanted to mention, not very many people know what laser actually means. Another question that has been asked by several of you, and I'm just going to answer it now as a broad sweeping answer, and that is, where do things change from being classical to being relativistic? At what speed Well, most of the time, we don't answer that as a speed, we answer it like this. When the energy of the particle is equal to or greater than its rest mass energy, it's a relativistic particle. If its kinetic energy is less than its rest mass energy, then it's a classical particle. I thought, let's do an example. Let's find out what is the rest mass energy of an electron. M naught C squared. Let's figure that out. Why don't you do it? I'll do it on the board quietly. You figure it out. Of course, we wanted in electron volts, not joules.
Which one? I'm just doing laser stuff. It's on the recording now.
And if you have to look up the mass of an electron, I'm going to come over there and slap you. Have the answer by now. M naught, like I say, I hope this is another familiar memory because it's a very important number. 9.1 times 10 to the minus 31 kilograms, that's the mass of the electron. The speed of light squared is 9 times 10 to the 16 meters squared per second squared. But we want electron volts, so we have to divide away joules. And I just quickly showed that the units work out nicely. So it's 9.1 times 9 divided by 1.6 times 10 to the, and if I do the arithmetic in my head, I get 10 to the plus 4, do you?
Yeah.
So you should not be dealing with the power of 10 in your calculator, just 9.1 times 9 divided by 1.6, and then when I move the decimal point again for deliberate reasons, I get 0.511 times 10 to the 6 electron volts, do you? Approximately, because that is really not the exact mass of the electron, nor is that the exact charge on the electron. But when you put in the two exact values, or as precisely as you can, you would get 0.511 times 10 to the 6 electron volts, which of course we call 0.511 MeV, mega electron volts. There's the rest mass energy of an electron. If you have an electron with this much energy or more, it's considered a relativistic electron. If it has less than this kinetic energy, it's a classical electron. So, for the fun of it, you might calculate what is the rest mass energy of a proton and a neutron, so that you can know what is the relativistic cutoff for those values, and write those on the inside cover of your book. Yes?
But this is an electron moving at C.
No, this is just the rest mass energy. No, it's not. I'm not saying the electron is moving at C, but remember, E equals mc squared. So the rest mass energy is the rest mass times the speed of light squared. It's not saying it's moving at the speed of light. So you can have an instant judgment criterion from now on. If the electron falls through 500,000 volts or more, it's going to be a relativistic electron. If the electron falls through less than 500,000 volts, it's going to be a classical. You need to know the values for the proton and the neutron. Why not calculate it once, write it on the inside pivot a little bit, and you can easily make the judgment from then on. Okay, so those were two little side notes that I put on my notes for today. That will be helpful. Understand what a laser is, understand the rest mass energy, and that's your judgment criterion from now on. If you're solving a problem which is a homework, quiz, or final exam, you're of course going to be asked to judge whether or not you need to do this relativistically. You now have a specific judgment criterion you can fall back on. So I give you a problem and you say, yes, its energy is greater than rest mass energy, therefore it's a relativistic. You've already earned a lot of points on the problem. Or if you say, no, it's not, it's less than the rest mass energy, you've earned a lot of points. If that's the only thing you do on a problem, you've earned points on the problem. If you don't do that, you've lost points on the problem. So from now on, I'm going to expect you to make the judgment criterion and tell me specifically what the answer is. Somebody was about to say something, cut you off?
Yeah, but you answered it.
I answered it as well, okay. Good. All right. This is a little bit of a review. De Broglie waves, the wavelength is equal to h over p. De Broglie's neat hypothesis was, if waves act like particles, particles must act like waves. If a particle has a momentum, it must have an associated de Broglie wave. He didn't say what it was a wave of. He just said it must have a wave. And it was later, 2 years later, that Max Born interpreted de Broglie waves. They are not physical waves. What are they? They are waves of what?
Probability.
That's correct. Probability. They are waves of probability. Do the waves have physical significance? No. We don't expect to be able to measure the wave directly. Physical significance? No. Why? Because a wave can become a negative or a positive thing, and there's no such thing as a negative probability. How can you have a negative probability? The worst you can have is a zero. That's the lowest probability. So it doesn't make any real physical sense to talk about psi. However, we have been talking about the wave function, and the absolute value of psi squared is called the probability density. And this does not suffer the earlier argument. This will always be 0 or greater, no matter what. And so this can be measured. This does have some kind of physical significance. Psi does not, but the absolute value of psi squared does. And we call it the probability density because it's proportional to finding the object. Proportional to the probability of the particle. And then I'll just put it here, x, y, z, t. And here's where I'm fond of simply saying the probability of finding the particle there, watching my fingers here, there, then. When you put in coordinates for the position and a moment in time, when you put in values for all 4 of these dimensions, then you can calculate this is proportional to the probability of finding the particle at that point in space, x, y, z, at that moment in time, t. Okay. Here's an interesting thing to notice. Look at this, and I'm going to ask you to reconcile at the end. So watch what I'm doing and see if you're willing to try to reconcile at the end. A wave's velocity, and right now we're going to call W the wave's velocity, of course, is the frequency times the wavelength. We know that for a long time ago. But it's a de Broglie wave, so the wavelength lambda is going to be what? H over the momentum mv. H over mv. And of course, the energy of an object like this, and de Broglie waves do seem to be massless particles. H nu equals mc squared. So here is going to be mc squared over h. So now let's calculate the velocity of the de Broglie wave. The velocity of the de Broglie wave is going to be mc squared over h times the wavelength lambda, which is h over mv. So of course we end up with c squared over v. Now here's the question, ladies and gentlemen. Certainly the v represents the velocity of the particle, not the wave, of the particle. So naturally then, that must be less than c, so w must be greater than c. How can we have, I thought Einstein said nothing can go faster than the speed. How can we have the de Broglie wave going faster than the speed of light? Because it's not a thing. Who said that? You're good. Get yourself a cookie afterwards. You deserve a cookie. It's not a thing. It's a wave. It's a de Broglie. It's a probability wave. It's a mathematical construct. So it's perfectly fine. Or, if you establish a certain situation by perhaps putting a particle within a restriction, then it establishes a de Broglie wave faster than light. In other words, if I somehow create I create an experiment, and you're quite distant away. I create an experiment. You're going to have to wait for light to carry to you the information that I've said at the experiment. So you're watching, maybe you're a light year away watching through your telescope. And I set up an experiment. It's going to take a year before you see the experiment, right? But the de Broglie wave is going to get to you faster than the light of the experiment. The de Broglie wave will already be established before you even know there's an experiment there. Because the de Broglie wave travels faster than light. So I just wanted to point that out and find out if you were thinking along these lines, and you are. That's very good.
Is the de Broglie wave only making measures without seeing the light?
Say again?
Is the de Broglie wave only making measures without the person?
You could measure the de Broglie wave, theoretically you could measure the de Broglie wave before you even knew the experiment was going on, yes. Did you have something? Same thing? Now, let's try to put all of this stuff to work, and the way I'm going to do this is here's the experiment I'm going to set up. The experiment is I'm going to put a particle in a box. We're going to end up really, on this first one, it's going to be a one-dimensional box. I'm going to draw it as a two-dimensional box. But there's a particle in a box whose dimension is just going to be L. That's the dimension of the box. The particle is here. It's going to strike the walls and bounce back and forth like that. Now the first thing, to make this a little bit easier to analyze, I like to analyze things only after everything has been established. So I'm not going to expect you to measure the de Broglie wave before you see the experiment. Essentially, we put the particle in the box and we wait for everything to stabilize, and then we look at it, and then we're going to analyze it. Now we're going to have to make a couple of assumptions to begin with. We're going to make these walls infinitely hard. They're infinitely hard walls. I often think about it like, imagine you had a ping pong ball inside of a steel box. Well, even that isn't a good analogy because the steel walls in the steel box are pretty strong, but these are infinitely hard walls. Second thing, all collisions are perfectly elastic, meaning there's no energy loss. So the particle, as it bounces back and forth, it's not going to lose any energy and therefore no speed. It's just going to move back and forth with constant speed. Everything is in steady state, nothing is changing, and the velocity is much, much less than the speed of light. So it's a classical problem, particle in a box. And let's see how this knowledge of the de Broglie situation will allow us to begin to analyze the particle in the box. The particle is trapped in the box, and it's moving back and forth with constant speed. As far as the de Broglie wave is concerned, this is a standing wave. So once you've reached steady state, the particle is moving back and forth, and the probability of finding the particle at any point in the box doesn't change. So that's a standing wave. It's a non-changing wave. So we have a standing wave. If that's true, then the first thing we know is that psi must equal 0 at the walls. Oops. The walls. In other words, since the walls are perfectly hard, they're going to reflect the particle. You're not going to find the particle at the wall. It's between the walls only. So, in terms of wave lingo that we've been using in the past, the walls are nodes. And, of course, that's the only restriction. Therefore, if I was going to draw a picture, this represents the two walls of the one-dimensional box. I should have written that 1D. It's a one-dimensional box only. Then, of course, we could have this situation. Here is what I'm going to call psi 1, and lambda 1 is going to be twice the length of the system. And of course, since the energy depends on frequency, that's the lowest energy, that's the lowest allowed energy, lowest frequency we have. We could also have the next possibility, which you have seen in your past, where we have this standing wave, psi 2, and here lambda 2 is equal to L. And of course the next one, psi 3, and lambda 3 is equal to 2L over 3, like it is. And of course, there's an infinite number of possibilities. But they are discrete possibilities. It's not a continuum, it is a set of discrete possibilities. So, lambda sub n is going to be 2L over n. Those are all of the allowed wavelengths. But, can I put it in here? No, I'm not going to squeeze it down. I'm going to move it down to the other side. But we can begin to discuss the kinetic energies of the particles, of the particle, the allowed kinetic energies of the particles in the box. Because kinetic energy, we know it's classical, so kinetic energy will be written down in the simple classical formula, but of course that's going to be mv squared over 2m. We'll write it like that. And we have now that lambda is equal to h over mv, so mv is h over lambda. And so putting in then for lambda squared is what? 4L squared over n squared. 4L squared over n squared. And you can see that I'm going to have a lambda squared right here. So the kinetic energy is going to equal mv squared, which is going to be h squared over lambda squared, h squared over lambda squared, 4L squared, and then I'll put an n squared on the top. Where am I? Divided by 2m. So we have, bring the n out, n squared times h squared over 8ml squared. So now I can subscript the kinetic energy. We have certain discrete allowed kinetic energies. And all of a sudden we see that the de Broglie hypothesis leads to the conclusion that we will always have quantized kinetic energies in terms of n squared times some. You know, really this is a constant, right? Because it's a certain particle, it's in a certain box, and all the rest of that is constant, so it's n squared times a constant. Now I have an in-class problem for you. This one is going to be kind of fun. And as soon as you get it, I'm going to start calculating it on the board because of the time. So I calculate the velocity of the thing, and I get 3.3 times 10 to the minus 31 meters per second. I wonder if I'll notice that velocity. I wonder if it'll look stationary to me. So I asked myself, how long will I have to conduct this experiment to actually see the marble cross the box? The time it's going to take is the distance divided by the velocity. It's going to take about 3 times 10 to the 29 seconds to do this experiment. That sounds kind of long, doesn't it? I think I'll have to go to the bathroom or something in between. I don't think I'm going to be able to spend all the time there. So I calculated it, and guess what? It's almost a trillion times longer than the time since the Big Bang. So it'll take a trillion times longer than all the time that's ever existed for this particle to cross this box. I don't think I'm going to be able to distinguish this velocity. Do you?
No.
This claims the particle is not at rest and it'll take a trillion Big Bangs to cross the box. Oh, all I can say is, oh, I can't do that experiment. See you on Wednesday. You can put those right here on top of the solution, please. Yeah.
Either of them. I know it's not my calculations, because I can see my calculations on here.
Yeah.
Oh, I think I know.
That's everything.